Welcome to DockerCon 22. This is the next chapter of a series of talks that started at DockerCon 2018. Depend on Docker means that the only tool you need to get from source to running software is Docker. Today, we'll see how Docker Desktop was used to develop a PyTorch-based predictive modeling application locally and deployed to Kubernetes at scale. My name is Alex Yankolski. I'm a Docker captain and a principal solutions architect at AWS. Please note that even though the materials presented here may be aligned with AWS, they should not be treated as formal statements and represent my views and opinions. In today's presentation, we'll first review some good reasons to depend on Docker. Then, we'll define some terms related to self-managed predictive modeling. We'll then dive deep into a demonstration on how to use the recently open-sourced aws-do-pm project to develop, debug, and run a predictive modeling application. And we'll end with some takeaways. Why depend on Docker? In my opinion, and I think most people will agree, using Docker accelerates innovation, boosts productivity, encapsulates third-party dependencies, and allows developers to run their projects locally for fast iterations while they're developing, then deploy in the cloud and scale globally. A lot of people in the world depend on Docker. It has become a tradition for the Docker CEO to announce the number of cumulative pulls from Docker Hub in the keynote at DockerCon. Over the years, I have collected these numbers and graphed them for you. It is astonishing to see this growth. There are about 8 billion people on Earth, and this year, the number of cumulative container image pulls from Docker Hub is at 489 billion. This is more than 60 times the entire Earth population, and is a good measure to show how much difference Docker has made in the world. Let's define some terms that we're using in this presentation. Self-managed refers to the preference to manage and have full control of your own technology stack rather than using managed services. A predictive model is a model used for forecasting of an asset behavior over time. A digital twin is a predictive model of an asset, and a level 4 digital twin is a predictive model that is continuously monitored and updated as new information becomes available. The Do framework linked here is a set of principles for building software and was used to develop all of the Depend on Docker projects from this series of talks, including the recently open-sourced aws-do-pm project, which is a template for building predictive modeling applications. Now let's dive into the demo. We'll build the aws-do-pm project using Docker, then review how to debug and step through the code using Docker Desktop and VS Code. We'll deploy the project on the AWS cloud using an elastic Kubernetes service cluster, and we'll demonstrate running L4 digital twins of a fleet of 1,000 electric vehicles. First, clone the GitHub repository by running the git clone command shown here. Then configure the project by using the pm command line interface, which is included in the root of the project. You can run pm config set to interactively walk through all of the settings essential for this project, including your AWS credentials, ECR registry, and target orchestrator Compose or Kubernetes. Next, build all the project containers by executing build.sh all. This project by default supports two target orchestrators, Docker Compose and Kubernetes. To run your containers on Kubernetes, you will have to set the registry setting in the project. Once the containers are built, you can run the project by simply executing the run.sh script. This by default brings up the system using Docker Compose. Status.sh shows the current status of the system, and exec.sh opens a shell into the platform container. The PM CLI is included in the container, and you can use --help with each of the PM modules to explore the functionality of the command line interface. Let's explore how to debug into the code. We can navigate to Source, PM, Task, and open task.py, which is core code that gets frequently executed. On comment line 26, you see that we're importing a package called debug.py, which we'll use for remote debugging on port 5678. Next, we'll exec into the platform pod and use the platform CLI to execute PM system init, which will execute some tasks, and as soon as this part of the code is executed, it will hold for us to attach the debugger. We use the Visual Studio Code remote attach capability to connect to localhost port 5678. We specify the location of the source code locally, and then click the green arrow button to attach the debugger. You can see the code is allowing us to step through line by line and explore the values of our variables. Let's continue with our local demo. You can use the CLI or the provided SDK to build predictive modeling applications. Run the ev-demo script. This is a sample application which uses the CLI to demonstrate all of the embedded core techniques in the system. It generates synthetic data for an electric vehicle, then registers the dataset and a training subset of data with the system, and builds an artificial neural network model, analyzes the model sensitivity, then deploys it as a gRPC service and keeps it up to date if the prediction error becomes greater than a predefined threshold. All of the system's operations are stored in a graph database. The local single vehicle EV demo running on Docker Compose usually completes within 4 minutes. If we're running the demo on a Cloud9 or EC2 instance, to explore the data, models, and graph, we need to expose the ports of the application UIs. We do that through editing the security group associated with the instance to allow SSH, and then opening SSH tunnels. We can use the platform UI to explore the data and models. This is a sample of generated data for an electric vehicle, and it comes with some charts, and this is how the battery drains over the course of a trip. This is the model sensitivity analysis, and this is information about the model and its accuracy. To explore the graph, we need to log into the graph database and then configure the graph labels to show the node names and load the full graph to display the entire operation of the EV demo run. If we want to deploy our predictive modeling application to a Kubernetes cluster and run it at scale, we need to push our Docker images to a container registry. By default, this project comes with support for ECR. To push the images, execute login.sh, ecr-setup.sh, and push.sh all. Next, let's scale up our pre-existing EKS cluster. We're going to do that by editing the autoscaling group. For visualization purposes, we use an open source tool called kubeops-view. We start from one node and scale the cluster up to 100 nodes to enable our demonstration to build models and run a simulation for a fleet of 1,000 electric vehicles. On this screen, we can see that our cluster now has 100 nodes. Next, we need to run pm-config set to configure our project for deployment to Kubernetes. Make sure to specify the target orchestrator as Kubernetes, as well as run the kcfg.sh script to configure access to the cluster. Execute run.sh to deploy aws-do-pm to Kubernetes. We have scaled our deployment to 50 platform pods. Each platform pod will run one parallel group of electric vehicles. We will use the 4 screens of our demo environment to set up monitoring. The lower right will show us the running tasks, the lower left will show the number of tasks running, and the upper left will show the number of deployed model services. In the upper right window, we exec into platform pod 1 and run pm-config set to ensure that the platform pods are configured within Kubernetes. Next, we will edit the EV fleet demo JSON configuration file and specify that each parallel group should have 20 vehicles. 50 groups, each with 20 vehicles, equals 1,000 vehicles total. To start the demo, just execute the EV fleet demo script. We can see that 50 parallel groups are being launched with 20 vehicles each and each vehicle driving up to 10 routes. Synthetic data is generated for each group and registered with the system. Then, an artificial neural network model is built for each group of vehicles and deployed as a service. Our cluster starts to work hard. We see the number of containers and the node utilization increase significantly. We now have 1,000 electric vehicle models, also known as digital twins, deployed and running in the system. They are being continuously updated as needed when new data comes in. Each vehicle drives between 5 and 10 routes. For each trip, a prediction task is created which runs in a pod against the vehicle model and predicts the battery drain for that trip. That is compared with the actual data extracted from the generated dataset. And if the error of the prediction is above the configured threshold, then the model for this vehicle is updated. As vehicles start completing their routes, we see the number of deployed model services start to decrease down from 1,000. The whole process takes about 29 minutes to complete. We can see this workload is ramping down. Eventually, both the number of deployed services and the number of running tasks becomes 0. We have successfully completed a run for 1,000 electric vehicles, each driving up to 10 routes. Next, we're ready to scale down the EKS cluster. We'll do that by editing the autoscaling group and setting the number of desired instances to 1. The cluster scales down, and we are left with 1 available node. Finally, let's explore the results by browsing the data, models, and generated graph. The platform UI displays data and model information similarly to the first demo, except we have a lot more data and models. EKS exposes the user interfaces using an application load balancer and ingress objects. By executing kubectl get ingress, we get the URLs by which we can access the user interfaces. It is interesting to visualize the behavior of the system by logging into the graph database and generating graphs from the tens of thousands of nodes and edges that are now available in the database. The dark gray nodes here are tasks, and the different colored dots are objects like techniques, models, datasets, and services. Here you can start your own predictive modeling project. In this presentation, we showed how to use Docker Desktop for fast development and debugging of Docker Compose and Kubernetes projects. We showed how to develop locally and deploy globally using containers. By showing our open source project built with Docker and PyTorch, we hope we have convinced you to depend on Docker and use aws-do-pm as a template for your self-managed predictive modeling applications. I want to express my appreciation to the following people for their contributions to the aws-do-pm project. And say a big thank you to the audience. Have a great DockerCon.